How to take game theory into linear optimization. Go back to the game we did last video, the Robinhood game, and we're minimizing the merchant's losses. So we'll call that the Q choices. So we minimize over the P choices. So when Q is 1, the minimum P, Q is 2, the minimum P, and then we maximize over the Q choices. So that's the pure choice, and the other way around. I maximize when P is 1, and I maximize when P is 2. And then I choose the minimum P choice. Nash equilibrium is what fixed this to an optimal strategy for both. This is optimal, of course, because of the min-max theorem. These two terms can never change places. The best they can be is equal. Let's rename our probabilities. So we'll set up for vectors and redo the thing using the Nash equilibrium model. Instead of minimizing over P, we look at the expected payoffs with our Q choices. And then instead of maximizing in Q, we just set those expectations equal and solve. Plugging those Q values in to the F, we get 10/3, our Nash equilibrium. And then we did the same for the Robinhood. Instead of maximizing, we looked at expected payoffs for the choices we could use. So we're looking at the transpose matrix. And then instead of minimizing on our P choices, we just set those expected payoffs equal and solved. And got our Nash equilibrium. To turn it into a linear program, we're going to look at the expected payoffs a little closer. Instead of minimizing over P, we're minimizing over these two numbers. One will be bigger than the other, and we'll pick the minimum. So we'll replace this pair with just one variable. There's no reason to have V1, we'll just use V2, and then there's no reason for V2, just call it V, and we want to maximize that value. And exactly the same on the other side. Instead of maximizing over Q, we're going to maximize over my expected values. One's bigger than the other. I'll just use W1. Well, then there's no reason to even have the 1. I'll just have a W. And then we minimize over that W. And there's our Nash equilibrium from both sides. To turn it into a linear program, I just put all the pieces in one place. Maximize over that scalar. So that scalar is a lower bound for every component of AQ. And then the Q's are a probability. Minimize the scalar W, so that W is an upper bound for A transpose P, and that the P's are a probability. It looks suggestive that these are dual problems, and in fact they are. Looking at the function that we are maximizing and minimizing, there's player 2's position and player 1's position. Go through the Nash equilibrium and we set up this. Every component bounded by V, and the Q's are a probability. Every component bounded by W, and the P's are a probability. Let's set up a new vector, the 1 vector, 1 in every component, so we can just kind of Make the notation a little nicer. Here's the clever bit we're going to do. We're going to change our max to a min and our min to a max through the reciprocal instead of through the negative. How come? We'll see immediately. I'm going to do a change of variable while I'll scale out the v. Change a variable while I'll scale out the w. Divide by v. I'll assume that v is positive. And substitute, which will give us a linear program in the canonical setting. And do a similar thing over here. Divide by w. If every entry in A is positive, v and w will be positive. So if you have entries of A that are not positive, just add the constant matrix until they are. This will not change the equilibrium position. And substitute. To show these are duals of each other, just run it through the Lagrangian, and it'll become apparent very quickly. It's an inequality, so I have to put in slack variables called surplus variables since it's a greater than. And there we are. They're duals. Positive constraint, new objective function.